In this lesson, we're going to learn how to really solve quadratic equations using the factoring methods that we learned last unit. But also, we're going to use this method to help us graph quadratic equations a more quick, at times, way than the table method that we learned at the beginning of the unit. So today we are finding quadratic equations by factoring. All right, to get us started, I want to take a quick look at a word problem that we will eventually get much more in depth with, but this just kind of gives you an idea of where we're going with this. So the path of Anika's golf ball through the air is modeled by the equation h equals negative 5t squared plus 70t, where h is the height in feet of the golf ball and t is the time in seconds. So we need a quadratic type equation for a scenario like this, because if you envision the path of a golf ball through the air, it's going up and then it's coming back down. And so this type of graph resembles what we know to be called a parabola, which is the graph of a quadratic equation. So in a parabola, and I knew it would be opening down for a couple reasons. First, when I see a golf ball go up in there and come back down, this is the path that it follows, and it's confirmed by that because the a value was negative 5. So it is opening down. So that brings us to this first question. How could we find the highest point of the golf ball? Well, visually, the highest point of the golf ball would be up here. Now, in quadratics, we have a special name for this point, and this point is called our vertex. And so here, for a scenario like this, finding the highest point, we could calculate the vertex. So remember, the vertex formula is x equals negative b over 2a. That gives us the x, and then you could solve for the y. So here a is negative 5, and b is 70. So negative 70 over 2 times negative 5 gives you x of 7, and then you could find the y by replacing each x with 7 and solving for y. And I'm sorry, I'm saying x when it is t and h. Whatever variable's in the place of x, that's your x, and whatever it's set equal to, that represents your y. We'll use other variables because of units occasionally, but they still represent your x and y points. So here to find the y, which is really the height, you can see here, it said that is our height. The x part tells us, okay, how far the ball goes before it hits that highest point, but the y is really the piece that tells us how high up it is on our y-axis. So we'll be solving for h, replacing each t, in this case, time, was 7. So here we would find the height to be 245 feet in the air. Lastly, just one other thing. Here in this case, because x is represented with t's and the time is in seconds, this tells us that it will take 7 seconds before the ball reaches that highest point in the air. So this ball went up really high in 7 seconds and then fell back down to the ground after that. So that's how our vertex is going to be useful to us in analyzing different quadratic type scenarios. The next piece we might be interested in looking at is when would the ball hit the ground? So if it's hitting the ground, this is another special point in a quadratic equation or on the graph of a parabola. Your parabolas will hit the ground often, not every time, but often in 2 points. In this case, her ball starts on the ground and it ends on the ground, and that should make sense. So to be able to answer this question, you have to really think about, well, what is a value that we know at the ground to always be true? So the ground is really when your height is 0 feet. You're not up in the air at all. You're at 0. So the height would be found by putting 0 in for h and solving for the time it would take for that to happen. Now here we see 2 zeros. The one that would represent hitting the ground after it's been hit is this one. So we would specifically be looking for that 0. So we've seen equations like this before where we would solve for t after setting equal to 0. And to do that, we would use the factoring methods. So today's lesson is all about factoring to solve for this special kind of point on our parabola. So just to quickly review before we get too much further, a quadratic equation is going to be slightly different than a quadratic function. And there's really not a huge difference other than just what it's set equal to. If I'm saying, okay, quadratic equation, we are setting it equal to 0 to solve it. If it's a function, we're just going to have that equal to y. That's the only difference there between a real equation versus function scenario. You might also see functions written as f of x. That works as well. So these just represent whatever your outputs are. Here we are specifically looking for when it's equal to 0. So when needed, we can interchange 0 for y depending on what we're looking for is the big reason we might be interested in knowing this. Okay, so quadratic solutions. The solution to a quadratic equation, or the solutions to a quadratic equation, are called the roots. So roots, so this is just a little vocab we need for today. The roots are where it, and by it I mean your quadratic equation, will cross the x-axis. These roots are also your x-intercepts. You can also call them x-intercepts. And so in that word problem we just started out with, your roots or x-intercepts are where that ball was on the ground. So in that scenario, your roots would represent where that ball landed or started from. So to solve a quadratic equation, we must set it equal to 0. Again, 0 being that starting and ending point. That's going to represent your roots and x-intercepts. So for example, if we're looking at this graph of a parabola, this will have two roots, two places where your graph crosses the x-axis. And finding these roots is going to be helpful in a lot of different word problem scenarios when we're analyzing these quadratic equations and functions and just different pieces about them. They're also going to be really helpful for graphing because if you find two roots, then that's going to really quickly tell you how wide the parabola will graph to be. And then you only need one other point, your vertex. So this will quickly diminish how many points you need to find to graph a quadratic equation. If you're using the table method, I'm going to ask that you're always graphing 5 points, one vertex, 2 to the left, 2 to the right. However, if you're graphing using the roots, you only need your vertex and your roots, and that should most of the time be enough information to be able to graph it. There will be a couple special occasions where that's not, and we'll get into what to do later in this lesson with those. So a quadratic can have 2, 1, or no roots, depending on how many times it crosses the x-axis. So in this first quadratic, and I hate that these don't have arrows because they do continue on, but my graphing thing doesn't put arrows on. Anyways, so here we have a graphed parabola. And remember, our roots are where it crosses the x-axis. So you can see this parabola crossing the x-axis 2 times. So this is an example of a quadratic with 2 roots. Here we have a quadratic graphed. However, it's only crossing or hitting the x-axis at 1 point. So in this case, we only have one root, and this is a special scenario because that one root is also, incidentally, your vertex. And lastly, a quadratic equation may have no roots at all, meaning it never crosses this x-axis. And here's an example of that over here with no roots, 0 roots. This doesn't mean you can't graph it. If we're in this situation, we would just set up a table to graph it, which is why we still need to know how to graph equations using the table method. And let me just reveal that, which is what I just talked about. Okay. So how to find our roots? There are going to be two ways this whole unit that we will be able to find our roots, which is also a fancy way of saying solving your quadratic equation. The first way to solve your quadratic equation is by using the factoring methods. So that's what we're going to be doing today, is reviewing how to use the factoring methods to help us solve for the roots of our quadratic. There are times where your factoring methods will not be enough to help you solve for a quadratic. So what I'm referring to here is, let's say your quadratic equation is prime, meaning it cannot factor. That doesn't mean it doesn't have roots, or that it can't be solved. Or can't be graphed. It just means that it can't be cleanly factored. So in that case, you would then use the quadratic formula. And we will learn about this method for solving quadratics later in the unit. Today we're focusing on the factoring methods. So like I was briefly touching on, quadratic formula will be useful to us when our equations are prime and cannot be factored. Only in that case will I allow you to eventually use this quadratic formula. I want you factoring these whenever possible, and only resorting to the formula when it's absolutely necessary. You will find that the formula is often a little more time intensive than the factoring methods if you're pretty good with your factoring methods. So we'll get to that later. So today, finding roots by factoring. So remember the factoring steps to solve equations. We always start by setting our equation to 0. So that may mean replacing y with 0, or just setting whatever your equation is equal to 0. From there, we will factor that side of our equation. And we will always look for GCF first, then look if it's 4 terms to do the grouping method. If it's 3 terms, then look at your trinomial methods, and finally look for difference of squares. Finally, set each factor equal to 0 and solve each factor. And that will give you your 1 or 2 possible roots for the graph. If there are no roots, that's going to be, at this time, a probably prime scenario. We're going to be looking at ones that have at least 1 root, though, today. And it doesn't mean if it has no roots that it's always prime. It just means, that it can't be graphed. It just means that we would need the formula later. Okay, so here we are with our first equation to solve. Find the roots of the following quadratic equation. So finding the roots is really a fancy way for saying solve this quadratic equation. Find where this quadratic equation would cross your x-axis. So we're starting with 8x squared minus 9x minus 5 equals 4 minus 3x. I accidentally already had step 1 shown, but we need to set it equal to 0. So that means bring those pieces over to the other side. So to get you 8x squared minus 6x minus 9 equals 0. At this point, we now focus on the left side of our equation and look to factor it. So I would check to see if it has a GCF. In this case, it does not. Now I'll look to see, okay, it is not 4 terms. We can't group it, so we move on to our trinomial methods. This one is a trinomial with a coefficient. So we'll take 8, the coefficient 8, and the final term -9, and multiply them together to get -72. We want factors of -72 that add up to our middle term's coefficient of -6. So that looks like -12 times 6 would add up to be a -6, which is what we're looking for. So we break our middle term, and this is a quick review of factoring by a trinomial with a coefficient, but we break our middle term into 2 terms and finish now with the grouping method. So hopefully you are cruising on this at this point in the school year and able to finish this factoring by grouping and get your 2 factors set equal to 0. Do notice I'm bringing down this equals 0 each time. From here, we are very close to being done, but we need to take each factor individually and set each factor equal to 0. So we'll start with 4x plus 3 equals 0 and solve for that x by subtracting 3 from both sides and then dividing both sides by 4, meaning that x is equal to negative 3/4 for that root. And for the other root, x would be equal to 3/2. So what this tells us is these are the points, the two places where your parabola will hit that x-axis. Remember, by setting it equal to 0, this is interchangeable with y. So what we're really doing is finding the points where you find your x value for a y value of 0. So this is really what those two solutions represent, are these 2 points. That means I could come here and plot these, and it's a little tight, on my x-axis as points. We now have 2 points for the parabola. You can tell because A is positive that it's going to be opening up. So lastly, to finish graphing this, if we wanted to, we would finish by finding the vertex. So remember that your vertex is found using x equals negative b over 2a. So you pull b and a from the point where it's in standard form, meaning it's set equal to 0. So a is 8, b is negative 6, and c is negative 9. Only when we've set it equal to 0 can we determine what a, b, and c are, because that's when it's in standard form. So for this vertex, we will then find x. Sorry, I've just revealed it, but negative b over 2a is negative 6. The opposite of negative 6 over 2 times 8. So that's your 6 over 16, which simplifies to your 3/8 for x. Then use x of 3/8 to substitute in for each x up here and solve for your y. Remember, you could change out that 0 for y. And so this gives you the point for the vertex. So lastly, if you wanted to plot your vertex, you can think about the decimal versions of these numbers. So our vertex here would be at around negative 10, about right here. And this is going to be enough to graph our quadratic. And we just have a nice little sketch, but we can see how narrow it is, how low that vertex is, and that it's opening up. So finding your 2 roots and then your vertex will be enough to graph quadratic equations by factoring. All right, let's do another problem. So here we have a squared minus 14a plus 3 equal to negative 10. We need to start by setting this equal to 0, so I'm going to undo the minus 10 by adding 10 to both sides. That gives us a squared minus 14a plus 13 equals 0. Next, we're looking for the roots, so we need to factor the left side of our equation. So a squared minus 14a plus 13, we need to factor this as a trinomial without a coefficient, so factors of 13 that add up to negative 14 would be negative 13 and negative 1. So you can set up your 2 binomials of a minus 13 and a minus 1. So those 2 factors set equal to 0. This one factors very quickly because there's no coefficient. And set each factor equal to 0 to find that a equals 13 and 1. So remember, these can be written as points. It is a, but this can technically be thought of as x each time. So this is the point 13, 0, and this is the point 1, 0. And so that tells you your 2 points, 1, 0, and 13, 0 is about out here. So we can see it's going to be a wide graph in this case. And finally, we would find our vertex to find the final point. This one will open up because a is positive, or the number times the x squared term is positive. So negative b over 2a, x equals negative b over 2a. So negative b over 2 times a. Looks like 14 over 2, which is 7. So the x is 7. We would substitute 7 in for x, or in this case a, everywhere in our equation and solve for y to get negative 36. So this is going to be at 1, 2, 3, 4, 5, 6, 7, way down here. I can't even fit it. But we would have a parabola that looks something like this. So nice quick sketch of that parabola. All right, here's your next one. Let's go ahead and go through this one together because this one has a special scenario that occurs. So here, step 1, set equal to 0, meaning we need to add 144 to both sides. Next, we're going to factor, and if you're really comfortable with your trinomial methods, hopefully you're noticing this is a perfect square trinomial, meaning the square root of 144 is 12, the square root of m squared is m, so 12 times m is 12m, and if you double that, you get the middle term. So this is a perfect square trinomial, which means it very quickly factors to the square root of m squared and then the square root of 144, both with the sign of the middle term. If you didn't see that, it's totally fine to just find your factors of 144 that add up to negative 24, which are negative 12 and negative 12. When you set each of these equal to 0, you find that the roots are actually the same. So what this really is indicating is that there's only one root. So 12, 0 is the only time this graph crosses your x-axis. And if you jog your memory back to the beginning of this video, we saw an example of that where there are times, oops, and I can't draw it up here. There are times where your parabola hits the x-axis at that special point of your vertex. So in this case, this actually is the vertex. If there is only one root, it is automatically your vertex. So without knowing it, we found our vertex right from factoring. So this is a special scenario if we wanted to continue graphing it. To help us graph it, we're gonna, we have the vertex. To finish graphing, we would actually need to set up a table. So this is a time where we can't really avoid the table method. We would then take some x values to the left, maybe like 11 and 10, and then take some values to the right, like 13 and 14, and find their corresponding y values. Do I have this graphed? Well, I don't. But it's going to open up, and then hopefully you would get a parabola opening up with your different points. So you would put 11 in for each m, solve for your y. In this case, we would replace 0 with y, get all these points and plot them. Okay, so we did that extensively in the last lesson, so I'm not going to go too far into this, but you would get some points, plot them, and sketch out the rest of your parabola. So this is a time where when your quadratic only has one root, to finish graphing it, you have to make a table and get several more points. Okay, if a quadratic can't be factored, so if your quadratic's prime, we will also use the graphing by table method to graph it. So just because a quadratic's prime, just remember that doesn't mean it cannot be graphed. It just means that the roots are not clean roots, meaning they're not nice whole numbers or integers or maybe clean fractions. And that's okay. It's just that if you recognize it can't be factored, you will need to graph using the longer method by setting up your table and finding your vertex. So just a couple reminders of that, and we've been reviewing this already today. Can I move this? There we go. The vertex formula. The x of it is x equals negative b over 2a. Use that x value to find the y value of your vertex. Set up your table with points to the left and to the right and plot your vertex and points. So that's just a quick review. And here's a quick review again of graphing quadratics. So if you want extra practice right now, I'd ask you to graph this quadratic equation by the table method. Click pause. When you're ready to check it, click play. Okay, so hopefully you've gone through practicing with the table method. You should have found your vertex to be -3/4, -17/8. Not a pretty vertex, which is where maybe using your calculator to store x as -3/4 to find y would have made finding the output easier. Then just pick some integers to the left and to the right. Remember, you don't have to use x values that are fractions in your table. Use easy to work with numbers. And your graph should have looked something like this with your vertex and then your points that you used, x and y, plotted. All right, and lastly, we saw this in the last lesson, remember you can check your vertex in your calculator by graphing the equation, then hitting Menu, Analyze Graph, and select Maximum or Minimum. If it's opening up, it's a minimum. If it's opening down, it's a maximum. Choose your lower and upper bound, click on both sides, and hit OK. You can also use your calculator to check your roots, which is really cool. So remember with this problem, we found our roots to be 13, 0, I believe, and 1, 0. So if we wanted to check this, we could use our calculator. Wait for it to come up. We would start by graphing this equation, just graph with x's for the a's. And once we graph, so let's come over here, we would graph our equation, there we go, as the x squared minus 14x, x squared minus 14x, and I believe plus 13. Don't worry about the equals 0 or anything, it's equal to y. And you can see this is really stretched out, so I'm going to zoom out actually. And there we go. So I can see the roots. And to check if these roots actually are 1 and 13 as we found them to be, what we'll do is hit Menu, Analyze Graph, and this time you'll select Find the 0. And by finding 0, that's implying find where it crosses the x-axis because the y's are 0. So Menu, Analyze Graph. This time we're not doing min or max. We're not worrying about the vertex. We're looking for a 0. We'll click once to the left of the first 0 and once to the right of the 0. And the point 1, 0 pops up. To check the other root, I'll do Menu, Analyze Graph again, 0 again. Click once to the left, once to the right of the other root, and I find that one to be 13, 0 as well. So this is just a really cool little trick to use after you're done to check that the roots you found actually are the correct roots for the graph of this equation. So lots of ways our calculator is useful to us in checking our work this unit. That takes us to the end of our lesson for today on graphing quadratics by factoring. Thanks.